Good afternoon. Thank you for coming to the first nuclear engineering colloquium of this semester. And Philip Stark is going to talk to us about a Noob's Guide to Reproducibility, which I personally am very excited about. But a little bit about Philip Stark is he's a professor of statistics, and he's the Associate Dean of Mathematical and Physical Sciences. And he works on inverse problems, uncertainty quantification, with applications such as astrophysics, cosmology, ecology, education, elections, food, geophysics, health, legislation, litigation, inverse. So he looks at a wide variety of problems, but they're all informed from the same kind of place. And in addition, Philip is one of the co-Is of the Berkeley Institute for Data Science and has a strong role in the reproducibility initiative there, which is part of what sparked all this idea. And for anybody doing science of any sort, reproducibility really is pretty essential. So without further ado.
Thanks a lot. So, thanks for inviting me to do this. I'm glad that the seats aren't all full. This is actually going to be a great opportunity for me to embarrass myself. There are at least 8 people I know in the audience know far more about this topic than I do, and in fact I learned much of what I knew from some of them. So I hope that they'll chime in and correct whatever I do incorrectly, because in the spirit of openness and reproducibility, we air our errors and let others fix them, right? Make sport of it even. I mean, the first disclaimer is I'm the newbie. This is not a guide for newbies, this is a guide by a newbie. And that among other people, I owe much to Fernando, to Lorena, Jared Millman, Aaron Kulich, Yael Benimini, for different parts of this, for teaching me pieces of it, ranging from how to think about it to down in the dirt skills. So I want to talk a little bit about what it means to work reproducibly, why we should, what makes it hard, what we might have to do, what makes it easier, and what's sort of the first, next, easiest thing you can do to move further down the path, or that I can do to move further down the path in my own practice, and then what can we do to try to move our disciplines, the university, science as a whole, a little bit further down the path. So in a nutshell, reproducibility is show your work. Right? This is what we've had to do since grade school. Somehow, when it comes time to publish in a journal, we no longer show our work. So what evidence are we actually presenting that what we did was the right thing to do, or that we even did what we claim we did? Again, to elaborate just slightly, we want to provide evidence that we're right, not just to claim that we're right. Science should be show me, not trust me. And again, what's happened in much of science is it's devolved into trust me. The journal articles don't contain enough information to be able to check things. And as a result, we're basically saying trust me. David Donahoe said that much of computational science, sort of published computational science, is not the actual scholarship. It's an advertisement for the scholarship. The scholarship consists of the software and so forth and so on that's behind the publication. I'd like to sort of flip that when it comes time to do things like evaluate people for faculty positions or promotions or postdocs or whatever, and say, how nice that you advertised your work in Science and Nature and so forth and so on. Where's your work? I'd like to look at your work. And somehow if we can move the ball in that direction, I think that things will be better for science as a whole. So the goal is to enable others to check whether your tables and figures result from doing what you said you did to the data you claim to have done it to. And that includes being able to check, what was the verbal description? Does the math match the verbal description? What were the data? What was the code? Does the code match the math, match the verbal description? Can you reproduce the figures and tables? And this is really mostly about computational reproducibility, right? This is somehow, can you recompute the stuff that was computed there? And if there is a good enough evidence trail, you can also assess, was it the right thing to do in the first place? So most of what I'm talking about is not reproducibility in the scientific sense, it's reproducibility in the computational sense. It's not the statistical sense, but the computational sense. But I'll talk a little bit about statistical reproducibility at the end if I have time. So again, a lot of this is about leaving breadcrumbs, showing your work. Right, why should you bother to do this? My top reasons are so other people can check my work and correct it if it's wrong, and so other people can reuse and extend my work more easily. And by others, I also mean myself next week. And I don't know how many of you have had the experience of writing some really clever code to solve a wonderful problem and then realizing 3 or 4 months later that there's something else you could do with that code and digging out the code and finding that you no longer have any idea how it works. Anybody else done that? Yeah, most of the people in the audience. All right. Okay, so why would we not want to do this? So the kinds of obstacles and excuses that we hear are, well, it's a lot of trouble. I don't get any credit for it. I don't get, it doesn't increase my citations or this or that. It doesn't count as a referee publication. How can it possibly be important because the whole discipline doesn't really place any emphasis on it? It's going to be really hard. I'm going to have to work differently. If I publish my data and my code, somebody else is going to get publications out of my data. I'm going to get scooped. Or they're going to be able to leverage the code that I did, and they're going to get the publication instead of me. Maybe I made a mistake, and I'm going to be publicly humiliated because other people will notice my mistake. Maybe my data have privacy issues, if it's medical data or something. Maybe there's intellectual property rights in the data, or a data moratorium from some particular experiment. I don't really know what tools to use to do this. I'm going to have to learn something new. I don't know how I can support a data set this size or put a fat enough pipe in for other people to be able to read it or get it. The journals aren't going to let me publish the code or the data anyway. I only get 17 lines in this highly prestigious journal to explain my entire story. There's no standards for doing this. What does it mean to be reproducible? I'm not even sure what reproducible versus replicable or auditable or, I mean, there's a whole long list of adjectives that people apply to work in various ways, and there's not much agreement. In fact, the terms are very highly overloaded, and you'll find exactly the same term means something quite different in a different discipline. Repeatable versus replicable versus reproducible, right? What's repeatable? Do you, in your discipline, do you have a notion of repeatability? Anybody have a repeatable notion? Nobody? Replicable? Yeah. What's your working definition of replicable?
Basically, we go to the UK Data Archive, we get the same set of data out, we run the set of models with the same software, and it looks the same, but we forgot to set our seed to the same as the guy who, and then everything looks crazy. Okay, so just the definition of replicable is if you started with the same data and ran the code again and set the seed to the same seed, would you get the same pictures, the same figures and tables? Okay, that's very different from if you ran the same experiment again in the laboratory using the same reagents or the same genetic clones of the mice that you used or whatever, would they behave the same way? Right? And that's even different from if somebody else did it in a different lab where the mice were sleeping in different bedding and being handled by women instead of by men, would the mice behave the same way? Right? So there are all these notions and they're heavily overlooked. Lorena, you were going to say something?
Yes, that in fact my use of full replication is different from that, which illustrates your point. And I would use the word reproducible for what you just said, and apply replication to the idea of coming to the same scientific findings, but collecting new data and using independent methods altogether. So what you replicate is the finding, not the process. But just to illustrate that different groups might be using the words in different ways.
And they do. So these terms are very much overloaded and inconsistently across disciplines. So ultimately, presumably what we're really interested in is what is the right level of abstraction so that if I describe things in these terms, I've actually described reality relatively accurately, but my scientific conclusions generalize in a particular way, and what are the limits of that ability to generalize? But in order to do that, you'd like to at least be able to generate the same figures and tables, starting with the same data. All right, we'll babble on from here. So Victoria Stodden did this survey of participants at NIPS, which is a machine learning conference, about why people didn't make their code available or didn't make their data available. So the left column is the percentage of people who gave that response with respect to code. The right column is the percentage of people who respondents who gave that response with respect to data. So if you notice, the top reason for both is the time to document and clean up. So 77% of the respondents, this isn't some random sample of people, it is what it is, right? But 77% of people said the reason that they didn't provide their code is how long it would take to document it and clean it up. So how many people in here code? Write code? Like just about everybody? Okay. One of the fundamental things I've noticed about my own code is if I can't read it and if I haven't documented it well, it's almost surely wrong. So I think that if you feel that it's going to take you a long time to document your code and clean it up, you probably should not trust the output of your own code, much less be writing papers based on that. That somehow it's just not good hygiene, not good work habits. Right? Okay, so that's an odd reason for not doing it, in my mind. It really means you're not contemplating your navel enough. Okay, dealing with questions from users. It's a lot of trouble to tell people what I'm actually doing and explain my work to other people. Not receiving attribution, that gets in the 40% for most for the respondents to that. Possibility of patents, not high. Legal barriers, somewhere in there. Potential loss of future publications, about a third of people for both things. So that's sort of fear of being scooped in some sense. So as competitors may get an advantage. It's kind of technical limitations seems to be low on the list. But if you look at these things, I would summarize them as fear, greed, ignorance, and sloth. Okay, so maybe we can behave better along these axes. All right, so I try to. It's sport for me to try to figure out pithy ways to say something so that you can't think about it the same way afterwards. I'm not very good at it, but I'm working at it hard. So this idea that, I'm not going to expose my work because somebody might find out that I'm wrong and that will be embarrassing, right? So if I say just trust me and I'm wrong, I'm untrustworthy, right? If I say here's my work and it's wrong, I'm honest and human and I'm really trying to further science. Right? There's no embarrassment in being wrong. The embarrassment is in pretending you're infallible and hiding your errors. Right? It should be anyway. So I hope that. Okay. In talking a little bit about software, this is an interesting abstract. Rampant software errors undermine scientific results. This was published in F1000 a little over a year ago. Errors in scientific results due to software bugs are not limited to a few high-profile cases that lead to retractions or widely reported. I estimate that, in fact, most scientific results are probably wrong if data have passed through a computer. And that these errors may remain largely undetected. The opportunities for both subtle and profound errors in software and data management are boundless, yet they remain surprisingly underappreciated. Okay. Okay, so let me back up there. I meant to tell a couple of stories first. So one of my former graduate students and I worked on a particular problem, estimating spectra from time series with gaps, and our method caught on a little bit and got used by the GONG project, which is this network of solar telescopes that are trying to estimate the normal mode frequencies of the sun and things like that. And I thought we had done a really good job of being transparent and open because we had published not just the paper and the underlying math, but some MATLAB code. And now I kind of cringe at the idea that I was using a proprietary software base for it, and also some CMEX files, sort of compiled C that mates with the MATLAB to make this stuff run faster, and we put all of that stuff on the web. Okay, so a couple of years ago, I guess the first time this happened was now about 5 years ago, and it's happened a couple of times since. Somebody came and said, oh, those CMEX files, they don't work anymore with the current version of MATLAB. Could we have your source C so that we can recompile this stuff and build this again? So we go and start digging into the tar archives of whatever we had there. Can't find the source code, can't find the source code. Imola found the floppy disks on which her dissertation was written in 1999, right? Cannot find the source code for this stuff. Okay, so something is, right? It's like there's somewhere along the line I will fail, right? I just will. Anyway, okay. So I hope it's right. I'm glad it's been useful to people. I'm glad they're still interested in it. But now we got to start from scratch. Okay, what can we do better most easily. So first of all, data analysis needs to be scripted. Shouldn't be relying on point-and-click tools, at least for your final analysis. You want to go do some exploratory data analysis with a point-and-click tool, great. But at the end of the day, if you relied on a point-and-click tool for your final analysis, you will have no idea what you actually did, and no way to tell other people what you actually did. And I'll say especially spreadsheet calculations. Spreadsheets are wrong. I'll get to more of that in a minute. Using revision control systems. Anybody who who does software development uses revision control. How many scientists use revision control? Very, very small. How many people here in the room do? Like half my arm goes up, because I now am getting much more religious about it. Okay. Documentation. Can you read your code? No. Then why would anybody else be able to read your code? Can you read your code today? Sort of. Then you won't be able to read it 2 months from now, right? It's somehow that the ratio of comments to lines of code should probably be fairly high unless you're writing in such a transparent fashion that the code is basically self-documenting, and that requires a lot of discipline to sort of not be clever and find the cutest way of doing something, but instead to be transparent and find the most obvious way of doing something, the most obviously self-explanatory way of doing something. Adhering to coding standards and conventions. Using pair programming. Who here has done pair programming? Who here has never heard of pair programming? Okay, so the idea is 2 people work together, a pair of people, and there's 2 sets of eyeballs on the screen, 1 person typing. And you're figuring out together what to do, and you're brainstorming together about strategies for what you're trying to do and noticing errors as they happen and coming up with better things in the moment. Better characterization of that? That's about right? Okay. Using issue trackers. Oh, I know I didn't quite figure out the right way to do it. I know that there's some corner cases I haven't dealt with yet. I ought to make a note. Not just in a comment line in the code, but a note someplace where I'm going to see it again, even if I don't visit that part of the code again. Using code reviews. Having other people's eyeballs on your code in a formal way when you try to explain what the code is doing to somebody else. And this is not just in the course of doing science, but in the course of teaching things. We need to be willing to spend the effort to grade students based on their code, not just on their output. And I've certainly been guilty of this in the past, that was sort of like, oh, the figure looks right, whatever, or the number's right, whatever. But it's not enough. Using code tests, unit tests, integration tests, coverage tests, regression tests. Are those familiar terms to everybody? Anybody want those explained? Maybe they should be explained by somebody who knows what they are instead of me. No. So unit tests are you're doing things in a modular way. Here's a piece of code. Does it do what I expect it to do? Right? Can I test this unit and verify that it gives the expected output in some number of cases? Integration tests are, do the different units work correctly together? They're not guaranteed to. Code coverage test is checking whether your tests checked your code. What percentage of the lines of code actually got hit by the tests? Are there big blocks of code that your test didn't check? Regression tests, I introduce a new feature. Great, my new feature works well. Did I now just lose some old features accidentally? Okay, is that approximately right? Okay, all right. So this is a great example of the difference between unit testing and integration testing. The unit testing is perfect. The integration test, not so much. Okay, back to ranting about spreadsheets. So they might be okay for data entry, but not for calculations. And this is they conflate input, output, code, and presentation. They make it very easy to make errors, and they make it very hard to find the errors. Very hard to debug spreadsheets. Very hard to do unit testing, coverage tests, any of these sorts of things. According to KPMG and PricewaterhouseCoopers, over 90% of corporate spreadsheets have errors. Okay, that's doing well compared to what the previous thing about scientific software said, right? I'm not sure who's being optimistic or pessimistic. And it's not just errors in building your spreadsheet. The underlying software is buggy. Excel in the past has had errors in addition, multiplication, random number generation, and statistical routines. The bugs in the random number generator persisted for several generations of Excel. So Excel claimed to implement the Wickman-Hill pseudo-random number generator. So that's a combination of linear congruential generators. It's not a very good one. It's actually not adequate for statistics. For statistics, you want something stronger like the Mersenne twister. For cryptography, you need something even stronger than that. But the Wickman-Hill, the code base for Wickman-Hill is probably about a dozen lines of virtual basic, since that's what Excel is doing it in. It's not a very good pseudo-random number generator, but it is supposed to generate numbers between 0 and 1. And Excel would periodically throw you a negative number. Okay, so there's clearly an implementation bug, but they don't allow you to seed the random number generator, so there's no way to reproduce the error. Okay, this is clearly a problem, and if you want to, okay. So, how did that? Stress tests of the international banking system are basically Excel simulations being run on supercomputers, often using that buggy pseudo-random number generator. I've actually heard somebody claim that the fact that the PRNG throws a negative number from time to time is great because it gives you a more stressful test, right? Somehow, is the whole results robust? Okay, insanity. This actually frightens me. I find that, okay. So here's my attempt to hack your limbic system again. Relying on spreadsheets for important calculations is like driving drunk. No matter how carefully you do it, a wreck is likely. Right? It's just really hard. Okay. So on to a short checklist of things that we can do. This I find useful for me to move the reproducibility, computational reproducibility of my work a little bit further. Finding the first place in this list where I fail is the thing to focus on next, all right? Don't use spreadsheets for calculations. Script your analyses, including the data cleaning and munging. That's more trouble than it sounds like. If you've gone through by hand to look at odd points and find things that weren't formatted correctly and so forth, you get a data set from somewhere, it has some odd characters in it, it's supposed to be a comma-separated value file, but it has different numbers of entries on different rows, or it comes as an Excel spreadsheet, and somebody is basically, there's headers and there's footers, and then there's other tables interspersed with this and that, and you kind of really want to cut and paste from that file to start to get a real CSV. Automating that is not always easy, right? Scripting that is not always easy. Anybody have any hints as to how to do that better? Yeah.
I would start doing it. I would not try to clean it up and then script it. I would have a script and I would grow it one line at a time.
So you would have a script that starts with your Excel spreadsheet and first strips out the header, and then
I would not have I'd have a CSV or something, but.
Yeah, so often, at least in some disciplines, people distribute data as spreadsheets. So this is somehow your input for your analysis, and getting the data out of the spreadsheet in a good way is not always easy. I don't know, for example, what Python libraries there are for reading an arbitrary spreadsheet and stripping the data out of a sheet of the spreadsheet, ignoring everything else. Are there good libraries for that?
So there is an Excel reader.
I know there's an Excel reader, but I'm not sure exactly
what some of that.
Gives you. Yeah.
I haven't used it in anger.
I know that Stephen Jenkins at the LSE has written a lot in Stata for this sort of stripping.
Okay.
The economists always distribute in spreadsheets.
Interesting. All right. So that's not necessarily an easy thing to do, and it might not be the first thing you do, but ultimately you would like to have the whole thing automated so somebody else can reproduce it, and it doesn't rely on your ability to cut and paste. Okay, cut and paste errors and selection errors in Excel. People familiar with the Reinhardt and Rogoff study and whatnot? So they wrote a book on economics, and one of their results was on the debt ratios at the level of nations and what that did to local economies, and they basically decided there's some bright line. If the debt ratio gets too big, things are going to get into trouble. And this was used to justify the austerity measures in Southern Europe, in Greece and Spain, etc. It was not peer-reviewed. Not that I'm saying peer review is the be-all and end-all, but it was also not open. It was basically a book, and what they did was hidden in some Excel spreadsheet that they were not releasing to the world. Some industrious graduate student, does somebody remember his name or her name? Or any,
the name of it, U Michigan, I think.
Yeah.
But I don't remember the name.
So tried to replicate, couldn't replicate, eventually got them to produce their underlying spreadsheet, and it turned out that they were wrong. And the reason that, apparently the reason that they were wrong is when they were developing their spreadsheet, they developed it with some set of nations, and then had eventually extended the data set to include additional countries, and had forgotten to increase the selection for the formula in the Excel spreadsheet, and it actually, I think, resulted in a sign error. That in fact, the whole justification for the austerity measures was an Excel error. Is that approximately right? Yep, okay. All right, so cut and paste, not so much. Record and report document your code. Yeah, we all have so much fun doing that, but honestly, if you can't read it, why do you trust it? That it's really somehow got to be that. Record and report software versions, including library dependencies. There are some tools that can make that an awful lot easier. But if you go to rerun your code next year and you get a different answer, why? I mean, is it because SciPy changed its calling signature for something, or I mean, it's just hard to know what happened if you haven't kept track of that. And if other people can't replicate what you're doing, they will not know. I mean, they'll have very little opportunity to diagnose why if you haven't given them enough information to check. Test the code: unit test, integration test, coverage test, etc. Avoid proprietary software that doesn't have an open source equivalent. And if you use proprietary software that does have an open source equivalent, it would be very nice to test whether your software gives the same, whether your code gives the same answer then. One of the biggest reasons that people seem to not do that is, this is the tool I learned in grad school, or this is the tool that's used in my discipline. Everybody uses Stata or MATLAB or Excel or something, and so on. Anyway, so report all the things you tried before getting to the answer that you liked. And this is now getting to issues of statistical reproducibility and whatnot. If you tried 47 different transformations of the variables, and linear regression and logit regression, and nearest neighbor clustering and classification regression trees and neural networks, and you finally got a picture that you liked in a little bitty p-value, your little bitty p-value is really, really misleading. It doesn't reflect what you actually did. It reflects the last thing you did, or the thing that you liked the best. And it is not an honest reflection of somehow the chance that under the null hypothesis is misspecified. The null hypothesis is not, if the correlation coefficient is really 0, what's the chance I would observe it to be this big? It's, if I tried all of these other things, what's the chance that any of them would have given a p-value that's small, right? And nothing, under something, nothing was going on. So it's really, really difficult to interpret results if you don't report the stuff that you did. Make the code and your code tests available to others. I'd like to see your code, and I'd also like to know how you tested it. Make the data available in an open format, provide a data dictionary. So I have seen data dictionaries that said things like the variable named mths_ovr, and the data dictionary said this means months over. Yeah, I could probably get that, but what is months over, right? I mean, so the data dictionaries that are absolutely useless. They don't tell you what the variable is. They just somehow unpack the name in a funny way. All right. And then finally, publish in open journals. And I'm getting more and more rigorous with myself about open publication. And I want to talk a little bit about why. Well, first, this is one of my personal bests. This is recently released with Ann Boring and Kelly Ottoboni. The code's on GitHub. As much of the data as we were allowed to release by law is on Merit. The publication is in Science Open. This is a post-refereed open publication format. And it's kind of fun watching the altmetric score go up. That's entertainment. All right, so why open publication? Well, I would argue, as would many other people, more eloquently than I will, that there's something deeply troubling about the current model for scientific publication. Our research is very often funded by government agencies or other foundations, et cetera. It's conducted at universities and businesses by faculty and grad students and undergrads, whatever. It's then refereed and edited for the journals by faculty, typically at no cost to the journal, right? They don't pay the peer editors or the peer referees. The faculty who wrote, or the scientists, I'm using the word faculty sort of generically to mean scientists, who write these papers and want them to be published generally are charged page charges by most journals. And then libraries or anybody who wants to read this thing need to buy the content back. This content that was produced at public expense, most of the heavy lifting involved in getting it into publishable format was done for free, and the journals are not just profiting on it, but they're making it inaccessible to most of the world, unavailable to most of the world. So I think that this is exclusionary and morally questionable. Actually, I would go beyond questionable. I think it's wrong. All right. So I had trouble getting this to quite the right scale, but this is a plot from the Association of Research Libraries of what's happened to library costs for various things between 1986 and 2016. Some of this is summarized and discussed in the Commission on the Future of the UC Berkeley Libraries, and there's a link to it there. Harrison, you can probably testify to some of this, but that thing has grown the most rapidly, that over that period has grown by 475%, is the ongoing expenditure for journals, okay, in both print and electronic format. The overall costs have gone up by about 188%, but that is the single thing that is driving library budgets more than anything else. I think, is it something like 60% of UC Berkeley Library's budget goes to periodicals? And most of those are for scientific periodicals. They're the expensive ones. Right? Am I?
That sounds like it's in the ballpark.
Yeah. Okay. We shouldn't have to buy the content back. We produce the content. Right? We shouldn't have to buy it back. And not only do we produce it, but we produced it at public expense. All right. So what's the role of the journal? I mean, it ought to have a gatekeeping quality control function by editors and peers. It helps with distribution and marketing, making your work visible to the world. And it provides archival functions. Okay? And I would argue that it's failing miserably at the gatekeeping function, and it's largely unnecessary for the other two functions. I think that very public retractions of major work makes it clear that even in very prestigious journals, the gatekeeping function isn't being performed very well. Now that's in part because the work itself is not reproducible, that there's no way that the referees and editors can possibly tell whether a lot of science that's being submitted is right or wrong, because they're not given the stuff. They don't have the code, they don't have the data, they can't rerun the, there's just no way, right? So their hands are tied, but nonetheless, it's an issue. Okay, what are some of the alternatives to publishing in journals like that, or what can we do to somehow break this cycle? The whole UC Office of the President this last year basically made it part of our employment contract that the university has a royalty-free license to all of our published work for the purpose of making it accessible, openly accessible to the rest of the world. So this means that you can freely sign away the copyright to your work to Science or Nature or the New England Journal of Irreproducible Results, positive results, I guess is probably better. Knowing that despite the fact that you signed it, you can still put it on the web, you can still put it into UC Archive, et cetera, because your contract with UC predates, in some sense, your publication of this work. And so MIT has been doing this for years and years. And so it's sort of a workaround to sort of, in effect, be able to provide open access to anything you do, unless you explicitly waive it. And you do have permission to waive it in particular cases. Also, which is kind of something that's kind of surprising to me, is the journals are presumed to know that this is the case if you work at UC Berkeley. You don't have to give them notice that you have already signed your rights away to somebody else. That's kind of surprising, but evidently that's true according to the lawyers. Okay, but that's one thing, is you can post things to the web or put them in archive or SSRN or whatever your favorite thing is in other repositories. You can pay open access charges to some of the journals that have open access policies. There's just this funny tension between saying, oh, this paper of mine is really good, I'm going to put it in a prestigious journal, and this paper of mine maybe is not that great, so I'm just not going to worry too much about it, I'll put it in the open access journal, right? So, because at the end of the day, the way that we're assessed for promotions, jobs, so forth and so on, very often substitutes the letterhead of the journal for an actual appraisal of the quality of our work. And I would like to see us not abdicate our responsibility as scholars to actually assess the scholarship by simply turning it over to citation counts, publication counts, and impact factors, right? That's just not the right thing to do. Okay. All right, so statistical reproducibility. What does it mean to reproduce a scientific result? So you go off in your laboratory and you run some experiment, and you find that the mice who get your treatment do X, or you have some estimate of effect size and a confidence interval. I go off and try to do the same thing. I get some other estimate of effect size and some other confidence interval. Did I replicate you or not? Right? How do you decide whether something is a replication? You could say, well, do the confidence intervals overlap? That's something that people sometimes do, if you have an estimate of effect size and a confidence interval. That's actually not statistically sound, at least not without some adjustment. The question is somehow whether a confidence interval for the difference in the two measured effects includes 0, rather than do the two confidence intervals for the effect overlap. It's a different statistical question. Does that make sense? But at any rate, suppose it isn't something where there's an effect size. Suppose you just get a p-value. I get a p-value for the absence of an effect in a particular setup model, whatever, of 0.03. You do it and you get a p-value of 0.1. Did you replicate or not? Okay. There's actually some subtle statistics in here, and there's some work going on in that direction on things called the R value and other stuff that are worth having a look at. P-hacking. So I kind of hinted at this before. If you try a zillion things until you get a picture that you like or a p-value that's really small or whatever, and then you say, voila, I have a small p-value, time to publish. Your small p-value does not really reflect your uncertainty. It doesn't. It's misleading, and it's going to be misleadingly small. Straw man null hypotheses. Very often, you'll see people do tests, even if they only do one test. It'll be something like, I have a group of people. I randomize them into 2 groups. I give one of them control, the other treatment, and now I find a confidence interval for the effect of the treatment by using a t-test. Okay? What's the justification for using a t-test? So a t-test would be the right thing to do if I had 2 populations. I took a random sample from this population, a random sample for this population. I knew that the underlying populations had normal distributions on the variable that I cared about, right? or that my sample sizes were large enough compared to the skewness of the population, this or that, that the sample means would have effectively a normal distribution, and then I could use a t-test. I would also need to assume that the variances of the two populations were the same, but the means were possibly different. What does that have to do with taking one population, randomizing it into two groups? Very little, right? So the sort of testing that hypothesis in that way is setting up a straw man. Your null hypothesis just doesn't realistically correspond to reality. And so you can knock down a straw man often very easily because it's the wrong thing. I'll give you a slightly more concrete example in earthquake prediction. One of the ways people claim that their predictions are good is the following. They look at how well their predictions worked on historical seismicity, and then they say, how well would my predictions have worked on randomly generated seismicity coming from a particular stochastic model? So that stochastic model might be Poisson point process, or it might involve shuffling the times of earthquakes or something like that. Okay, so they hold the predictions fixed and they randomize seismicity. Right? What if you just have a bad model for seismicity? You may very easily reject the null hypothesis because your model is no good, not because your predictions are good. Okay? If you think about weather prediction, one of the best predictors there is, in most places, in many places it's actually about the best you can do, is to say that tomorrow's weather will be like today's. Essentially the same thing works for earthquakes. If there was an earthquake today, predict there will be one tomorrow. If there wasn't one today, predict there won't be one tomorrow. That actually works really, really well. Right? Earthquakes tend to be clustered in time and in space. So if my predictions exploit that by saying, here's an earthquake, predict there's going to be aftershocks, I can do pretty well with a predictor like that. Now what happens if I take those predictions and I now shuffle earthquakes in time? Those predictions are going to be horrible, right? I'm destroying the actual clustering in earthquakes. Right, okay, so, and in fact, that's what happens if you look at how these methods behave around, but they claim microscopic p-values because look at how well I do on the actual seismicity compared to random seismicity. No intelligent seismologist would ignore whether there was an earthquake yesterday in predicting whether there's going to be an earthquake tomorrow. But that test does, right? The test, okay. All right, changing endpoints in trials, this is a real problem. An awful lot of medical trials and experiments, they say we're going to set out to do this, we're going to measure the effect of blah, blah, blah on mortality, and they collect the data, and there's no effect on mortality, so they look at whether there's an effect on the length of your big toenail, or something, right? And so they look at all possible things. That's p-hacking, right? That's somehow mining significance so there's a wonderful entity that's like looking at what people said they were going to do as their endpoint and what they actually did in their published paper. And it's telling to look at that in this comparetrials.org thing. False discovery rate. This is wonderful statistical stuff pioneered by Yoav Benyamini and Yossi Hochberg. If you think about rejecting a null hypothesis as a scientific discovery, look, I can rule out that there's no effect. Okay? So that's a discovery. Voila, small p-value. Most statistical methods prior to what they did said, if I'm testing, they fell into one of two categories. Either you're saying every time I make a test, I'm only interested in whether that test gives an erroneous result. Okay, and I control the probability of a type 1 error, the probability of an incorrect rejection of a true null hypothesis. Alternatively, there's something called, so that's the per comparison error rate, or per test error rate. Alternatively, people look at things that they take a family of hypotheses and say, I'm going to test all of these hypotheses, and I'm interested in controlling the probability that I make one or more mistakes in testing any of these. That if they're all correct, what's the chance that I reject one or more one or more of the ones that is correct? What Benyamini and Hochberg did, which is really revolutionary, was the following. They said, no, let's look at the claimed discoveries. Let's look at the rejections. And what we really like to know is that in that pile of discoveries, the rate of those discoveries that are really wrong, the rate of false discoveries, is kept low, is kept under control. And they develop methods that allow you to control that rate even though you don't know how many of the discoveries really are true, really are false in the first place. It's kind of remarkable work. It's taken over large swaths of statistics. Moreover, they've shown that if everyone practiced science that way, then you could that would automatically control the whole discipline-wide false discovery rate. If you do it in your own work, if everybody did their own work, it somehow controls it. I wanted to harp just briefly on the difference between reproducibility and preproducibility. So preproducibility is my made-up word. Reproducibility ought to mean something like somebody else does it, can do it, and they can get the same answer. Well, leaving enough breadcrumbs for somebody else to try to do it is preproducibility, right? So it's the prerequisites that you need to try to reproduce what's going on. And somehow we've lost that distinction. We somehow think that my work is reproducible. Well, maybe it is, maybe it isn't, but I've given you all the tools to find out, right? I've given you all the information you need. Okay, so reproducibility in teaching. I've now switched to using Jupyter Notebooks and GitHub for my new teaching materials and my technical talks. Some examples there. Lorena has wonderful examples. This is a little snippet from AeroPython, where you can sort of mix mathematics, text, code, and output, including the graphics. GitHub will now render things in Python/Jupyter Notebooks in place. Jupyter now supports 40 languages, 40 programming languages?
55, I think, last we checked.
55 programming languages, probably including your favorite, provided your favorite is not proprietary.
Including some proprietary ones, actually, built by industry.
Interesting, okay. All right, so finally, I'm an old fogey already. I actually like coding and like learning new stuff, but in general, it's not as easy for me as it is for people with more malleable brains. So what's the solution to the problem that it's hard to teach an old dog new tricks? It's to work with the puppies, right? So education, I think, is probably the biggest lever that we have in moving things forward. And the education is actually a two-way street. In fact, I learn more from the puppies than I teach the puppies. When I'm working with the next generation of scientists, or maybe it's already a couple generations of scientists since my students have students, often they know more about these tools and practices than I do. In trying to build some courses around this and some education in different directions, we recently formalized a class in statistics 159/259, which is on reproducible and collaborative statistical data science. It's being taught this semester to the graduate students in the data science and the environment. No, it's DS4, it's data science for the 21st, not DSC 421. That was a typo. The master's capstone class in statistics now includes reproducibility. The PhD level applied statistics class now has topics on reproducibility. BIDS, the Berkeley Institute for Data Science, has a reproducibility working group. One of the deliverables from it coming very soon is a case study book that will draw from a variety of different, it would be examples from a broad spectrum of science, like how people try to incorporate reproducible practices. Many people in this room have contributed to that. There are other courses that are a little bit more accessible and less extensive, like the data carpentry and software carpentry courses. So this is the thing that I think would move the ball furthest, fastest, is if people pledged as follows. I will not referee any article that doesn't contain enough information to tell whether it's right. I get this from the journal. I will send it back with a polite note saying, I'm sorry, I can't tell if this is right or wrong. If you would like to send me the work to be able to evaluate the work, I would be glad to do that. Well, reluctantly, I would do it. Okay. Nor will I submit any article that doesn't have enough information to tell whether it's right or wrong for publication. And if you want to set some timeline, nor will I cite any work that I can't check if it's published after some date, like 2017. Okay? I think if we did this, we could make things a lot better really, really quickly. There's an open science peer review oath that's similar to this. I was pointed to it after I put this online. Okay. So what does it mean to work reproducibly? It means show your work. Why bother? Well, it's the right thing to do. Provides evidence that what you did is right. Promotes reuse of your work and you get wider reach. David Donahoe attributes a lot of the success of his work on signal processing and wavelets to the fact that he made his wavelet toolbox available to the world. John Claerbout, a geophysicist at Stanford, started having his PhD students have reproducible dissertations, that basically there was a make file for the whole dissertation, like make thesis. And what he found after doing that was that his students could build on previous students' work much, much more rapidly. Instead of it taking something like a year or to a year and a half to get useful work out of a PhD student, it would take a few weeks. So people could get up to speed much, much faster. They could see what other people had done. They could build on it. That's kind of a remarkable benefit. It benefits all of us, science, the discipline, fewer errors, faster progress, allowing other people to stand on our shoulders. What will it cost? Well, you might have to learn something. That's supposed to be our job. We need to learn new tools. No, but it does help, and your students might already know the tools. So if you encourage them to work reproducibly in your lab or whatever, you can get some trickle-up effects. Lots and lots of resources. I won't go through these, but they range from things for virtualization and reproducible environments for computing, to tools, to courses, so forth and so on. And you know, what's the simplest thing I can do? Try to adhere to the checklist or check your work with the checklist. Start a repo for your next project. If you haven't used revision control yet, start the next thing you do. Ask your students for help, because they probably know more than I do. What can I do to move things forward? The pledges, I think, are probably the biggest thing that we can do. Just don't referee work that you can't actually check, right? Okay, so then really important, don't use the journal masthead as a proxy for the work quality. Look at the work. Check the actual evidence that the work is good in hiring promotion cases. Don't bean count. Don't worry about the impact factor. Okay, thank you very much.
Thank you, that was wonderful. I'm sure we have some questions from the audience, so I'll let you field your own questions if you want to.
Sure, yeah.
Yeah, I guess I was wondering if you'd say a little bit more about the idea of a data dictionary. So is that effectively a text file describing what's in the data? That's just a new term.
Yeah, I mean it's metadata. It's it's explaining how the data are organized and what the variables mean. Yeah. Not just unpacking abbreviations, but actually saying, you know, that was the months by which this lasted more than something or other measured.
And that could be accomplished in a number of ways.
Lots
of ways.
A
Jupyter notebook, you could, when you import the data, like lay that out.
You can explain it. If you're archiving the data somewhere, you can have a text file that explains what it is. If you're doing things in you can have metadata of various kind actually embedded with the data set. You know, JSON still doesn't support comments, right? So I guess you could define a variable that is the comment, but that's kind of crazy. But XML kinds of things would let you have sort of self-documenting data sets and whatnot. Yes.
So I work at BITS, the Berkeley Initiative for Transparency in the Social Sciences. And you mentioned like the reasons why people don't publish their code or their data. And I think you can frame it sort of as you did, but I think that the quality of research shouldn't rely upon the goodwill of people, on people just on their own volition doing good things. I think I want it to be institutionalized, I want it to be required. And it seems like from my perspective, a lot of the issues are really just tenure review committees, where the incentives are not directing people to do their work in a transparent way. Meaning if I can be opaque, why spend the extra 100 hours or the extra 5 minutes on being transparent? You're a professor, do you have any idea what tenure review committees think about making this a criteria for tenure? Yeah, so I agree. I do think that the biggest thing that we can do is to, is this. That if when we are evaluating people for jobs or for tenure or whatever, we actually look at the work, not just look at the advertisement for the work. Again, it's like what I was saying at the beginning, like how nice that you advertised your work in Nature. So what? The problem is that the system has an awful lot of momentum. It's an enormous ship to steer. It does mean more work, not just for the scientists producing the results, but for the people evaluating the research. But it just seems like it so obviously needs to happen
right? That there's going to be an enormous train wreck. And we're seeing more and more casualties along the way. And at some point, I mean, certainly in the view of the public, science is getting less and less reliable, less and less trustworthy, in part as a result of our failure to actually do what would be recognized as science by, say, the Royal Society, you know, in the 1700s or whatever. I mean, it's just, it's supposed to be public. It's supposed to be, people are supposed to look over your shoulder and say, oh yeah, I see that that is actually what you did and why you got that answer. And it's not anymore.
Do you see your peers changing? Like you see cultural change among the rest of the faculty?
Yes, I'm seeing at least a recognition that there's an issue, and more senior faculty embracing reproducible practices in their labs by their students and postdocs, even if they're not going to learn the new tool themselves. There's something I wanted to say before and forgot to, which is this computational reproducibility thing, you know, certainly was a lot less of an issue before computers. But even when we had computers, when they were mainframes and people were sharing a software base, sharing a code base, everybody who's doing, you know, nonlinear PDE is using this one code on this one mainframe and, you know, an entire lab. It's much less of a problem than it is when everyone has his or her own computing device running a different version, different libraries, different this, different that. And so the problem has actually gotten bigger and bigger. In addition, the problem with data has gotten bigger and bigger because your data set isn't these 37 lines you can put on one page in a journal article. You know, it's petabytes of data that you don't have a fat enough pipe to move anywhere. Right? So it's getting harder.
Yeah, I'm visiting from the UK, where we've gone absolutely crazy in terms of citations, publications, totting up anything we possibly can through our assessment exercise, and we see no end to this anytime soon. At home, I'm always pushing for sort of micro-citation or micro-attribution, and there's no real system that we've found to do this easily. Do you have any thoughts that you might share with us?
Well, I mean, this is not my area of expertise. I should probably defer to Harrison or somebody else. But I mean, you can now get DOIs for all kinds of stuff. And there are entities popping up. There's one in Finland just getting started that's called something like GUAANA, which is painfully close to guano. But it's trying to give DOIs for ideas. You know, you sort of like you put your idea online and you can get a DOI for that. Science Open will give you a DOI for a review of an article published on Science Open, a non-anonymous review. So there are people, you know, doing that kind of thing. The thing is, at the end of the day, unless your assessment committee is simply counting the number of pages in your CV, somebody's got to look at it and figure out, is this important? Is it valuable? Is it novel? Is it fluff? Yeah. Other thoughts, Harrison? You?
I think the citation of things beyond the traditional published literature is still just, it's emerging. I mean, even just citation of data sets is still fairly rudimentary, and so it's hard to tell where things are going to go. So there aren't any standards, but certainly all the people doing work in altmetrics are looking at how to count other ways that scholars reference each other's work. So there's definitely people thinking about it and work going on. But yeah, I don't think we're anywhere close to being able to cite best practices. Sorry.
Yeah, just a quick comment on that. It's worth noting that GitHub now will allow you to assign a DOI to a piece of code if you make a formal release on it, which has two benefits. It first gives you a citable atom, the DOI, for metrics purposes, but it also encourages you to actually flag a specific tagged version of the repo with a concrete version number as the thing that used for replication, which makes it easier to say, I was using who knows which tag of the repo when I did this work, and if somebody tries to go back and it wasn't a specific version, you have to start bisecting inside of the history of that repo. And so it both serves the method purpose and encourages a better practice simultaneously, which is good because it has benefits for both. But I have a question for you, which is, in following on the question about committees on campus and things like that, what do you think is the role of the funding agencies, the federal funding agencies, et cetera, in helping bring some of this change about?
I don't know what their right and true role is. I can tell you what I wish they would do, which is simply to say, I'm sorry, journals, but you know, this was paid for by public money. It's got to be in the public domain. And I understand the desire to have a moratorium on data sets of some period of time, especially for enormous data sets. But I'm really uncomfortable even with things at CERN, the LHC experiment and whatnot, where their code base is proprietary, the data proprietary. They're using enormous sums of money, and why should I trust the result? That's how it's done. Anything else?
One quick question.
Yeah.
So how does this fit into the curriculum? So in other words, students have learned methodology for a long time, but what we're talking about now is almost like pre-methodology or
Yeah.
things that you need to know.
So I think that Jupyter is a really good example of a piece of technology. If we were working in a chemistry lab 20 years ago, we would have a little quad-ruled lab notebook, and we would be jotting down that we weighed this much of this and this much of that, and we put them together, and we cooked it at this temperature for this period of time, and then we measured what came out, and it was this. And the problem is that with computational science, and then if we wanted to say, how did I do that again? It's in your notebook, right? In computational science, we kind of have moved away from that, but technology like that lets you move back towards it. It's the equivalent of a lab notebook. So this is really somehow basic hygiene for doing data analysis computational science, and it ought to be, like taking college writing. It's not you bolt on this extra reproducibility thing to the work that you just did. It's we learned good penmanship once upon a time. We learned to brush our teeth. We learn to keep track of our work in some sensible way, and so that other people can read it. I think that if we can, in the curriculum, start looking at the students' work and not just the output, that'll make an enormous difference. As the next generation of faculty comes in who actually know how to do this stuff, that'll make a difference. And I think that for that to happen, one of the biggest things has to be for my generation to at least not be in their way.
All right, well, let's thank Philip one more time. Thank you. Next week, the nuclear engineering colloquium will be back in